Hey guys, this is going to be our video for section 6.6, which has to do with factoring and solving polynomials that have higher degrees than just 2. We've talked a lot about quadratics, especially in chapter 5, but now we're going to talk about some strategies we have for cubics, quartics, and so on. So stay tuned, buckle up. It's just going to be a lot of practice problems for the most part. So the first thing that we want to look at is remind ourselves of the strategies we already have. So greatest common factor, which in class oftentimes we've just referred to as, can we pull something out? Can we pull something out of everything? So on the screen there we have an expression on that left-hand side that says 32ab squared plus 2b cubed minus 4a squared b. And so the first thing we should look for still is is there a common factor that I can pull out of all three of those terms? And it looks like I could pull out a 2, and they all have at least one b. And so that would leave me on the inside with 16ab to the first, because I pulled out one of those b's, plus I pulled out the 2, so just b squared, minus 2a squared, I believe. And we can always check that by seeing if we distribute, if we multiply that 2b back in, will we get the original? So we would get 32ab squared plus 2b cubed minus 4a squared b. So it looks pretty good. That's our first strategy. We're still looking to try to just pull something out. Next, we want to just keep in mind, is this something we've maybe seen before? P squared minus 81. I'm hoping that you're to the point where you say, oh, that's a difference of 2 squares. I know how to factor that. P plus 9 times P minus 9. Remember, we had that formula. If we have two perfect squares and they're being subtracted, that always factors into square root of the first plus the square root of the second, square root of the first minus square root of the second. So that's one that we know how to do. Here's another one, kind of what I would consider just a typical chapter 5 quadratic. We can set up our parentheses. We know that the only way we're getting a squared is a times a. Signs are the same. They're both pluses. And 2 times 2, 2 plus 2, both add up to 4. So there we go. Maybe a little bit harder, but same idea. R squared plus 3r minus 18. Well, I know that it's going to be r and r. That lets us know that the signs are different, remember. So we have r plus something, r minus something. Multiply to be negative 18, add to be 3, 6 and negative 3. So 6 with the positive side, 3 with the minus side, and that should do it. And one more, just again, these are typical chapter 5s. X squared is x and x, minus and minus. Multiply to be 64, add to be negative 16, negative 8, negative 8. So these four are all things that we've seen before, that it's kind of assumed maybe we aren't perfect at, but we do know how to work these strategies. And so we do have a way to go about factoring these problems. But these are all a squareds or r squareds, x squareds. And so what if we have something like this and we're asked to factor it? A cubed minus 4a squared plus 3a minus 12. Well, you can see at the top there, the good news is we actually do have a strategy that can solve this, and that's grouping. We saw grouping in chapter 5 when we were trying to factor quadratics that had an a value other than 1. So here we have a cubic, it has 4 terms. We're just going to kind of follow the same procedure. Let's see where it takes us. We have 4 terms. So let's just say group them 2 by 2. What can I pull out of that group of 2? And change colors here, but it looks like this group of 2, we can say, we can pull out an a squared, leaving me with a minus 4. And then the other group of 2, it looks like I can pull out a positive 3, leaving me with a minus 4. And since the insides are the same, we're good to go. We can write the factors. One of them, if you remember, a squared plus 3, the things we pulled out. And then the other one is just a minus 4. And so we can use grouping, a kind of a technique we already know, to help factor cubic expressions. Try this one. I want you to try this one kind of on your own, pause the video, but group it 2 by 2. See what you can pull out. I know there are multiple variables, which makes it look more intimidating, but it should turn out kind of the same way. I'm going to pause the recording, work it on my own, and then we can both unpause and compare our answers. All right, so on my screen, you can see in blue my work and my answer for this one. On that first group of 2, I was able to pull out a 3a squared, leaving me with 2a minus 3b. Second group of 2, I was able to pull out a positive 2b, leaving me with that same 2a minus 3b. So my two factors, 3a squared plus 2b, what I pulled out, times 2a minus 3b, whatever was left inside both of them. So grouping, don't want to talk too much more about that because it's something we kind of already know. I did want to just give you one more reminder. This looks almost like an identical problem to the one we just worked, but it's not quite identical. If you look closely, you'll see the difference. And I just wanted to illustrate we can still group, but what happens on this second group? I know I want to end up with 2a minus 3b on the inside because they have to match for us to use grouping. So with that in mind, I'm going to pull out a negative 2b. And the reason I know to pull out that negative is because then it will leave me with positive 2a minus 3b. And so we can always pull out a negative if we need to make those factors match. So 3a squared minus 2b, 2a minus 3b. So just a quick side note, quick aside, we can pull a negative out to kind of make the signs work if we need to. So that's grouping. And so the good news is, like I said, that's something that we already know for the most part. This next thing to be on the lookout for is just strictly formulaic. It's kind of like when we had a difference of two squares. We saw that earlier. A squared minus b squared is a plus b, a minus b. Well, here we have two equations that allow us to factor the sum or difference of two perfect cubes. So you might want to take a second and pause the video and write these down because I know there are a lot of a's and b's on the screen right now. But what this is saying is if we have a cubed plus b cubed, two perfect cubes being added together, it will always simplify and factor, I should say, into the form the cube root of the first plus the cube root of the second, a plus b, times a squared minus ab plus b squared. Okay, so that's our sum of two cubes. The difference of two cubes right below it looks almost identical. It just starts with a minus b and then a squared plus ab plus b squared. So because these two formulas look really, really close, here's how I remember them. If you notice, a squared, a squared, ab, b squared, b squared. The kind of those variables and such, they don't change at all. They're the exact same between the two. So all we have to be on the lookout for is the signs. I'm also going to highlight this plus at the very end because it's plus on both of them. So these are identical formulas except for their signs in the first two spots. And so how do I remember? Well, if it's a sum of two cubes, I'm going to start with a plus and end up with a minus to balance things out. And if it's a difference of two cubes, if it's a minus, I'm going to start with that minus, a minus b, and then have a plus to balance things out, noting that the final sign is always plus. So just showing you what this looks like here, we have x cubed plus 27. First thing I would probably do is say, okay, is x cubed a perfect cubed? Yes, it's x cubed. So if it's x cubed, then a is x for our formula, this cube root of that first term. What about b? What does b equal? Well, 27 is a perfect cube, as it so happens it's 3 cubed. 3 times 3 times 3. b is 3. I know my formula is a, start with a plus because this was a sum, a squared minus to balance things out, and then plus always at the end. So now I can just plug things in. So x plus 3 times x squared minus 3x plus 9, it looks like. And that will be the factored form of that expression. The next one down, 27x cubed minus 8. Let's do the same thing. Can we write 27x cubed as something cubed? Well, 3 cubed would get us our 27. X cubed would give us our x cubed. So a equals 3x. Now b, what is cubed to get 8? That's 2. 2 times 2 times 2 is 8. So b is 2. I know that my formula starts with a minus because this is a difference, and then a plus to balance things out. So we're talking 3x minus 2 times, so what is 3x quantity squared? That would be 9x squared plus 6x's minus 4, it looks like. So factoring that difference of two perfect cubes, we just start with the minus, have a plus to balance things out, and oh my goodness, I almost forgot, this is a plus. Everything on the end is a plus, right? I wrote that as a minus because I was thinking difference, thinking about what I was going to say. That last sign is always a plus. So a minus b times a squared plus ab plus b squared. Again, these are just strictly formulaic things you want to know. Probably put a little bit of time into memorizing. Good news is we get 2 formulas for the price of 1, basically, because we don't, as long as we know the trick with the signs, the actual variables don't change in those formulas. So what I would like to do and we're a little over halfway through, but I want to pause because I know I'm throwing a lot of strategies at you. There are 4 problems on the screen here. And what I would like you to do is pause this video and use 4 different strategies to factor these. Look back at the notes, look back at the examples, say what kind of strategies do we have that we could use for these problems. Pause the video, take a stab at these and then unpause it, and I will have these kind of worked out and talk through them. So go ahead, pause the video and factor these 4 expressions. All right, so you can see my work on these 4 problems that are up on the screen right now. Top left in red, that was just a sum of 2 perfect cubes. So A was x, B was y, and plugging them into our formula that we just looked at. Top right, you might have looked at and said, wow, that's a lot of variables. I'm not sure what I can do with it. Well, the first thing we should always look for is, can we pull something out? We could pull out a 3ab in this case, leaving us with 3ab times 3ab squared plus b to the 4th minus 5a. Bottom left, whenever you see 4 terms, the first thing I usually think of is, I wonder if I'm supposed to group these. And on this problem, you were. On that first group, you could pull out an x, leaving you with x plus 3y. Second problem, you could pull out a 2y squared, leaving you with x plus 3y. And so both factors written together, x plus 2y squared, that's what we pulled out, times x plus 3y, that's what was still left inside. And then on the bottom right, I threw in there kind of a chapter 5 one, but a is not 1, so we still had to group. It's kind of another grouping one. Off to the right, you can see my work. A times c needs to equal negative 30. B needs to equal positive 7. So 10 and negative 3 are my numbers. Plug them in there, group 5x minus 1 times 3x plus 2. So this is kind of more indicative of what a lot of math going forward is going to look like. It won't just be use grouping for all these problems. You're going to have to know when to use grouping. Oh, I see 4 terms. I bet I need to group. And so knowing all these strategies and when to apply them is kind of that next challenge. There is another thing we're going to talk about today, and that is factoring polynomials in quadratic form. And so here we have a quartic, and it says factor completely. It's x to the 4th minus 13x squared plus 36. So thinking through our strategy so far, we say, well, we can't pull anything out. It's not really a grouping problem. It doesn't look like, it's not a sum or difference of two perfect cubes. So how do we attack this one? We're going to do this by something called quadratic form. We're going to make this look like a quadratic. We're going to make it look like an x squared or something, because that's what we'll be pretty familiar with. And here's what I'm going to do. I'm going to lead you through this first one, then we'll see lots of kind of how do we do this and when do we do this. I'm creating a brand new variable called u. And I'm saying u is just going to stand for x squared. Okay, so anytime I write u, it means x squared. Well, I know that this is x squared squared, because of our exponent rules, minus 13x squared plus 36. That means that I could just as easily write this as u squared minus 13u plus 36. Now that's something I can factor. That's basically a chapter 5 factoring problem. So I can set up my parentheses. I can say, okay, so that's u, and they're both minuses. Multiply to be 36, add to be negative 13, minus 9, minus 4. And so it looks like it's factored. We should never, though, if our problem is given to us with x's, we should never leave our final answer without x's. So I'm going to come here and say x squared minus 9, x squared minus 4. I'm going to substitute that x squared back in now that I have the u's all factored, taken care of. And you might look at this and say, wait, it said factor completely. I think I can factor this even further. Difference of two squares, x plus 3, x minus 3, x plus 2, x minus 2. So the idea behind quadratic form is let's write a higher degree polynomial as a quadratic. Let's use u substitution. We oftentimes use u. And plug u in so that it looks like a quadratic. We can factor it like a quadratic, and then just sub out that u at the end and plug, in this case, the x squareds back in. Okay? So here's another one. Try this one real quick. What should u be? Well, if I'm trying to put this as something squared, it would have to be g squared minus 29g squared plus 100. So it looks like u should be g squared. And that's because now I can see I'm going to have u squared minus 29u's plus 100. And there is a very standard chapter 5 quadratic for me to factor. I'll set up my parentheses, u minus minus. 25 times 4 is 100, and 25 plus 4, they're both negative, so that adds up to the negative 29u's. Now that u has served its purpose, I can sub the g squareds back in. And in this case, just like the last one, make sure to factor as far as you can. So g plus 5, g minus 5, g plus 2, g minus 2. We will factor those quadratics that we found after factoring the first part. So that's kind of the overview of quadratic form. Now, a natural question is, when can we use this? Can we use this anytime? Well, I want you to look at the two examples we just worked, and I'm going to point out a couple things and answer this question. We can only use quadratic form when the middle degree, in this case it was 2, x squared, is exactly half of that first degree. First degree was 4, second degree was 2, it's exactly half. So I can use quadratic form. Same thing here and there. So with that in mind, if possible, if the question is just put it in quadratic form if possible. We look at those two degrees, those two exponents, and we say a to the 8th, a squared. that's not going to work for quadratic form, because if we said this needs to be something squared, it would have to be a to the fourth. But we don't have, we can't put a to the fourth in there because it was just a squared. So this cannot work. And we can just say, okay, this one's not possible. We can't put this one in quadratic form. What about this one? Answer is yeah. Yeah, if we wanted to, we could say u equals, well, this would have to be 11 times something squared, so n cubed. And does that work here? Plus 44 n cubed. Yes, it does. And so I'm going to make my u equal n cubed. And so 11u plus u squared, excuse me, plus 44u. And so that is in quadratic form, 11u squared plus 44u, because again, that degree here, n cubed, so 3, was exactly half of the degree there, n to the 6th. All right, kind of a tricky-ish one here. Can we put that in quadratic form? At first glance, the answer is no, because we have b cubed, b to the 5th, 3 is not half of 5, and we might say no. But the answer is kind of yes, and here's why. What if I started with the step I always should start with when I'm trying to factor and pulled out a b? Well, now I'm left with b to the 4th, b squared, and a constant, which looks exactly like I would want it if I wanted to write this in quadratic form. Now, one quick thing here, I'm not going to write this in terms of u, because, you know, if I did, I would have u's inside here, but I would have a b on the outside here, and then that's mixing and matching our variables. It's a really minor thing, but I'm just going to write it in quadratic form, kind of like that in-between step that I've been doing, like this. And so why this is still considered quadratic form is it's still something squared plus that same something to the first plus a constant. And so this does qualify as quadratic form if you're wondering, even though we didn't substitute a different variable in. In the textbook, it actually shows mainly just like this. So this is how we can now attack x to the 4th quartics, or maybe even higher, like b to the 5th in this problem, and factor them out. So the only question left is, what do we do if we're asked to solve? And I want to make a quick note here, but it's a super important note. If we have x squared, we have two solutions. They may be real, they may be complex, imaginary, but we will have two solutions for every x squared polynomial. If it's x cubed, we should have 3 solutions. If it's x to the 5th, we should have 5 solutions. If it's x to the 12th, we should have 12 solutions. So looking at this, your first instinct might be, oh, I'm just going to take the cube root of both sides here. And what is the cube root of -8? Can we even do that? Well, what times itself equals -8? -2 times -2 times -2. Because +4 times another -2 would equal -8. You might be tempted to do this and just say, oh, x equals -2, done. The problem is you're only 1/3 right. This is an x cubed. We know we should get 3 solutions. So here's what I'm going to do. How can I factor this? It looks to me like if I move that 8, this is a sum of 2 perfect cubes. And if you remember back, I mean, we've talked about a lot today, but x, so let me write out my a and my b. A is x, that's the cube root of that. B is 2, the cube root of that. So x plus 2, start off with a plus, x squared minus 2x to balance things out, and then always a plus on the end. 2 squared is 4. So that's factored. And I can see that one of my answers is -2. But I need 2 other answers. And so I need to say, what would make this factor equal 0? And we have some strategies for that. That's the good news. It's a quadratic now. We could use quadratic formula. We could use completing the square. I'll do completing the square. I kind of like completing the square. So I'm trying to figure out what would make x squared minus 2x plus 4 equal 0. So x squared minus 2x, and then plus blank equals negative 4 plus blank. If you remember, we want to put b over 2 squared up there in my blank, so negative 2 over 2 squared, I need to put a 1 on both sides. That gets me to x minus 1 squared, and I'm going through this quickly because we should already know it, equals negative 3. Square root of both of those, x minus 1 equals plus or minus I root 3, should recognize that. And so x equals 1 plus or minus I root 3. And so if you look at this problem, we do have 3 solutions now. We have negative 2 in red. We have 1 plus I root 3. That's a complex solution. It uses that imaginary number. And we have 1 minus I root 3, also a complex solution. But those are my 3 solutions for this x cubed that I knew I needed to find. So how would I describe solving these? Take your original equation and think of what factoring strategy do we know of to factor it, to break it down. In this case, it was the sum of 2 cubes. And then on the left-hand side, it was really easy, x equals negative 2. On the right-hand side, I was then left with the quadratic. So I said, what strategies do I have to factor or solve quadratics? And it turned out I just ended up completing the square on this one to find those other 2 values of x. So that's a great representative problem there. And then here's another one that I just put on here. I know we kind of solved this one already, except we didn't. We factored it. And so you see that x to the 4th, you see x squared, and you're like, oh, those degrees are, that x squared is half the degree of x to the 4th. This is probably a u substitution, a quadratic form one. So I'll say u equals x squared, because this would be x squared squared minus 29 x squared plus 100 equals 0. So u squared minus 29u plus 100 equals 0. Which means, as we did before, I'll set up my parentheses, u minus 25 times 4. And now that we got the u's broken down, we can sub back in our x squareds. X squared minus 25, x squared minus 4 equals 0. X plus 5, difference of 2 squares, so x plus 5, x minus 5, x plus 2, x minus 2 equals 0. So x equals, what would make each of these equal 0 on their own? Negative 5, positive 5, negative 2, positive 2. And going back to that comment I made just a little bit ago, this was x to the 4th. We should see 4 solutions. And we do. If you wanted to write it, I know some of you guys like writing it kind of shorthand, plus or minus 5, plus or minus 2. So guys, I know this was a lot of problems thrown at you in this video, and it ended up being kind of long, but these are the kinds of strategies and skills we now have to factor and solve higher ordered polynomials. We started out with things we've seen before, kind of including grouping, but grouping now in like an a cubed sort of sense for cubics or things like that. We had these 2 formulas for sums or differences of 2 perfect cubes. Did some practice there. And then this last method was quadratic form. Can we take, a u variable, create it, and set it to something so that we can write our original expression as a quadratic? Can only do that if the second degree is half of the first degree. And then just throwing that final piece of the puzzle in there, solving, just like chapter 5, just means after you factored it, find x values to make it equal 0, make each individual factor equal 0, with now the piece of knowledge that you might have picked up on. If it's x cubed, it will have 3 solutions. If it's x to the 13th, it will have 13 solutions. So the number of solutions, both real and complex, added up together, should be the same as the degree of what we're working with. So guys, you will have practice problems on this. You will get the chance to kind of work this out and hopefully ask questions. If you had questions from this video, hopefully you wrote them down. If not, do so now so you can ask them when we next meet. But in the meantime, get lots of practice with these different factoring methods and know what you have at your disposal so that you can always use the easiest method for the problem at hand. Guys, that's it for this 6.6 video. I will see you next time.